So we'll start fresh with stochastic gradient, mini-batch stochastic gradient descent. So I suggest, like, whatever is being written on this slide, I suggest you just go through it once in your mind. Okay, I have written it descriptively, so such that I don't forget the important points I want to tell. Fine. So I think we last class we talked about matrix multiplication. We talked about matrix multiplication, and we talked that there are three ways to multiply two matrices. First is like switch off this light is coming. So what we take, first row and the first column. Okay, first row and first column. But that we will see today that it is the slowest one. That it is the slowest one. It is the slowest one. Then what you can do is efficiently decrease the computational time. How you decrease the computational time? You take two different matrices, multiply this A matrix with the first column of matrix B. That way also you can multiply matrices. And that is possible because suppose this is n cross n and this is also n cross n, then this column should be of n row one column. And you can here because this matches with this. So therefore it will give you one more vector. Okay. So therefore this multiplication is also possible, column wise or row wise computation. And this is a bit better than the first one. Fine. So why it is better? You can see it keeps only one column in the cache. So reducing memory access overhead. Okay. But in the first case, it was fetching the entire row and the column repeatedly. In the first case, always the first row and the first column, first row, second column, all the times you were keeping that in the cache. First row, second row, third row. That is very much computationally inefficient. So therefore, if you do this one, rather you take one column at a time in your cache. So therefore, there will be n columns here, and there is just one matrix here. So therefore, you are working with n columns as opposed to the previous case. So therefore, you can see why the second part is better than the first part. The third case is the best one. Like you can see, it is the best, but it's a challenging one. Just compute A equals to BC directly. Okay, just give it to your computer and yeah, it will do it. But how it does, yeah, that's still not known. Fine. Other is block matrix multiplication. Block matrix multiplication, I hope many of you in your bachelor's studies, you might have encountered in linear algebra or anywhere, okay, that you see something like blocks. Suppose I have this big matrix. If I have a very big matrix, 100 cross 100 here, but let me write this small one. So So can you see, like, you can actually write it in block format? How you can write it in block format? Just observe that one block here is the identity. So therefore, you can write this matrix as some I and some remaining elements. So dividing the matrix into blocks, like dividing the matrix into blocks. So like that, you can take out the matrix multiplication. Okay, so that is known as a blocked matrix multiplication. So divide the matrices into smaller sub matrices or blocks and perform multiplication on those. This improves your cache locality, reducing memory bandwidth usage, and computational efficiency is increased. Okay. So I suggest you just Google these if you don't know these optimized libraries. Okay, just to have some knowledge about this. So therefore, why we came to a very important concept that is known as vectorization. I gave you one example of a color-coded heat map plot plus. So there, I told you that that is very computationally expensive because each pixel to compute takes, if 1 minute, suppose each pixel has this 1000 cross 1000 matrix, okay, and each pixel you are color coding with some data, like some ideas, okay. So suppose each such pixel takes around, how much do you expect? 1 minute. Suppose 1 minute. Then how much time do you expect this whole program to run? 10 to the power 3 into 10 to the power 3 number of grid points into 1 minute. Because here 1000, here 1000. So how much minutes is it? How much hours? How much hours is it? How, okay. So it is more than a day, I think. More than of course it's more than a day. More than 2 days also. Okay, I hope. More than 3 days also. I hope. Okay. So therefore, that is very much time consuming, isn't it? So how you want to do it? Vectorization. Rather than just computing each pixel and color coding it, I suggest a different way, a different approach. That is, at one instance, like the same matrix multiplication case, how you were multiplying the whole matrix with one vector, one column vector. Similarly, here, you just compute all the columns at one stretch. Each columns at one stretch. It will evaluate each column at a stretch. And suppose how many columns you will have? How many columns? 1000 columns. 1000 columns you will have because you have 1000 rows and 1000 columns. So 1000 columns you have. But it will reduce some time, but not that efficient. But if we have written the code in terms of vectorization, like this, not pixel wise, okay, carefully. If you have written your code or program in a way that it doesn't compute it in a for loop pixel wise, rather than as a column wise operation, whole column, okay, then you will be able to parallelize it. Okay, otherwise you cannot. So you cannot write any code and use it in parallel. It has to be written in vectorized format to make it parallel. What does it mean to make it parallel? You give each, so I told you in the class that you take the halwa, okay, and you want to distribute in the class, what you do? That full halwa, like you cut into pieces, you count how many students are there first, and that many cuts you want to make. You don't want to make more cuts because then people will get less area halwa, right? That is not efficient. You want to eat more. So therefore, you count the number of people and that many cuts you can make. Okay, fine. So therefore, here also, like you made 1000 cuts and you have to give 1000 cuts to each of the processor. What is the processor in your case? Stomach was the processor. So in this case, each column will be given to one processor to compute. So what is the processor name? It will be one CPUs. It will be one CPUs. Okay, it will be each CPU. Fine. So 1000 CPUs you give. 1000 CPUs you give, and 1000 column will be taking how much time? 1000 minutes. 1000 minutes. So each CPU takes 1000 minutes. Okay, and there are 1000 such CPUs. So all will complete the job at what time? Hmm? All will complete the job in what time? Huh? Huh? Carefully. Each column consists of how many elements? 1000 elements. Each element takes how much time? 1 minute. So 1000 elements will take 1000 minutes. Okay. And each column you are giving to one CPU. Okay. So that will do the job in 1000 minutes. Second CPU will also do the job in 1000 minutes because those CPUs are independent. Okay. Similarly, 1000th column will do the job in 1000 minutes. So all the CPUs will finish the job at what time? 1000 minutes. So within 1000 minutes, you are able to finish the full job. So only 1000 minutes. Previously, how much amount you took? 10 to the power 6. That is 10 to the power 3 times more. 10 to the power 3 times more. Do you agree? Do you agree what is happening here? Yes. So can you see that doing parallelization, you are able to reduce the computational load by the amount of 10 to the power 3. 10 to the power 3 times you have reduced your computational time. So therefore, that was a major breakthrough in my work also. That was a major breakthrough in my work also. So I had to color code one big matrix. Okay, and if I do that, only I can complete my PhD. I think I was telling this story, is it? So therefore, if I did 1000 cross 1000 by manually instead of vectorization, then it would have taken 10 to the power 6 minutes for me. And I had to generate 4 such plots. So 4 into 10 to the power 6 minutes. Okay. And maybe I don't have that much amount of time. How much you can calculate and tell me. That is. So therefore, I did vectorization. That means dealing with vectors. So when you are writing a code, you are tempted to write in a code such that individual calculations are done in a for loop. Don't fall into the trap. Okay. You can maximize your efficiency of the code. Write the code in such a way that you can take vectors at once. And multiply the vectors at once. Okay. Vectors means you are taking, I will tell you to very nice example. Suppose you are shifting a house, your all house belongings. What you do? You have one, what do you call that? One jar you have, big jar you have. Okay, that is there. And small boxes are there here and there. Some box is there, some book is there, pen stand is there, some laptop is there, something is there. So how you will take it? You have one empty box and all these things. How you will it? Will you take the laptop first? Keep there. Small things keep there. Or one thing is there, that is one empty box is there. There you put all the things and take that empty box. Second one is much more efficient. Yes. So that's the same thing you are doing here. What you are doing here, when you put all the things into that jar, you are taking a vector. Vector means a collection of elements. So that means if you collect your elements and make some computations, it is much more faster rather than taking individual elements with you. So therefore, this is always you will use it in our daily life. But when it comes to computational something like that, we use for loop to do individual multiplication. I was also doing when I was in your time. So therefore, but when you know that vectorization is actually powerful, then you should shift the way you are writing your code. That will make it much more fast. We'll see that. So therefore, vectorization enables this CPU or GPU to process multiple elements simultaneously. So you can use this optimization libraries and which ensures that matrix operation use highly efficient implementations. Okay. So if you use NumPy, if you use TensorFlow, MXNet, so all these are, so therefore you see most of the times TensorFlow is used in most of the applications. In your bridge course also, I started to talk about the difference between PyTorch and TensorFlow a bit in your bridge course. Okay. So therefore, if you use these packages, then it is much more, you are safe zone that you can know that whatever computation it is doing, it is considering the most efficient, computationally efficient routine in its algorithms. Okay. Fine. So yeah, these already you know. Let's start with this. So Minibatch. Okay. So we'll come to matrix multiplication as a Python code in this class and show the use of Minibatch. So what we did in stochastic gradient descent, in gradient descent, we computed for all the training samples, we computed the gradient at once. We computed the gradient of all the training samples at once. How? We took the average of the gradient of all those training samples. N training samples. So you just took 1 by n summation grad fi. And that is grad f. I equals to 1 to n number of training samples you have. Okay. That is gradient descent. What is stochastic gradient descent? Rather than considering all the averaging out of throughout all of your training samples, randomly pick up one of the training samples at every iteration. Okay, so instead of this first example, you just write grad fi. That's it. At every of your iteration, just pick randomly. I is picked randomly. Okay. So all of this. So then we came to know with replacement, without replacement last class. We saw both of them are efficient according to their own use. Okay. So if you use with replacement, then it introduces higher variance in your gradient. Okay, because the same element can be chosen more than once. Okay, this is one of the most important questions. With replacement, without replacement. Okay, it's fine. So now we come to mini-batch stochastic gradient descent. So what it does is, first of all, I think we'll talk about a bit of computational efficiency. So processing single observations require multiple matrix vector multiplications, which are computationally expensive, we saw. Okay. So therefore, mini batches allows us to perform these computation more efficiently by processing multiple observations at once. The same thing I told you, like if you can do multiple columns given to multiple CPUs at once, we are able to reduce 10 to the power 3 times the computational time. So therefore, mini batch, it helps you to perform these computation efficiently by processing multiple batches at once. Okay. So how we can compute the gradient in case of mini batch stochastic gradient descent? Okay. So simple case, we'll see. So as usual to stochastic gradient descent, you have to take only one observation at a time. One observation at a time. That is one computing gradient of one sample at a time. Okay. So you can see we are when using a single observation. In mini batch also you are taking a single observation. Fine. But some modification is there. So therefore single observation I am denoting by xt. Then the gradient is given by gt. Gt means t is the time, like gradient at that time instant. Gradient at that time instant. Or since we are iterating it, I would suggest gn. That is nth step, like gradient at nth step. So t or n you can use. It doesn't matter much. Okay, it's just a notation. So this is just I have written like partial derivative because this xt will be a vector. Xt will be a vector. X1, X2, X3, X4, Xn. How many nodes you have in your neural network? How many nodes you have in your neural network? That depends. Okay, this concept will be clear when I come to regression. This concept will be a bit more clear when I come to regression. Okay, right. So this is just, and this is the weight u, w, sorry. Weight is also a vector because corresponding to each xi, there is a weight associated wi. Okay. So therefore, the dimension of x is same as the dimension of w. Okay, we'll see. We'll see. It is not mandatory that you understand all the steps here carefully, but as you progress through the course, you will make connections. So the idea is simple. Many things you might not understand in this, but when I come to regression, you will remember these things and make a correlation. Okay. So therefore, just keep this in mind. Just keep the basic idea in mind. Okay. So this is just the GT, which computes the gradient of the sample XT. Okay, of the training sample XT. Okay. So instead, why not use a mini batch? So this is what the difference is. We use a mini batch that is BT, mini batch BT, and the size of the mini batch is just by taking the modulus mod BT. Okay, the size of that batch. How many samples you are considering in that batch is essential. Then for that batch, okay, so we average over multiple observations. That means here, what you are doing, can you just look into the formula and understand what we are doing here? So I told you last class also, suppose you have 3 batches. This is your data set X. This is your whole training sample X. Okay. And what you are doing, you are dividing the training samples, suppose n samples, into bins. I hope you have read about binning in data analytics. Binning. Okay. It's the same way of technique as binning. Okay. You bin it. So what you do, you just divide the number of training samples into batches of 3 batches. Suppose I'm giving you example of 3 batch, and you have suppose 60 training samples. Suppose so each batch maybe you can do 20. Okay. So size mod B1 is 20. Fine. Is it okay? Okay. So here what we are doing, we are just averaging the gradient over each batch. Compute the gradient for this batch, this batch, this batch, and average it over. Okay, that's the exact thing we are doing here. See, the denominator has the size of each batch and the summation f of xiw. Okay, so this is the gradient only. That is dw is there. So therefore it is a gradient only. No need to confuse that it's a function. Okay. So I belongs to BT. So I belongs to BT means how many 20 number of samples are here? I belongs to, if you are in B1, then I should belong to those 20 samples. Okay, fine. And you are averaging it out. That's the same way as batch, mini batch. It should give you a reminiscence of the actual gradient descent method. Because in actual gradient descent, you don't batch it. You just take 1 by capital N. 1 by capital N summation of grad fi, which I wrote it here. Can you see some similarity between this equation and this equation? Okay. So we are doing the average. We are just doing the average in both the cases, but in this case, in equation 2, we are doing mini batch. That means averaging over the batches. Okay. So turns out that this comes with experimentation actually. No one knows that if you do batch wise, then it will reduce computation. It is all just trial and error method, like just intuition you have that if you do in batches, will it reduce computational size? And then you know that yes, it indeed reduces computational size. Then it becomes a good method. Okay. So that is about mini batch. So why we need to use mini batch? So some statistical benefits, like you can see, since the mini batch is here also you are doing it randomly, like how the elements in each batch is taken care, how elements of each batch is taken care. That is also random because you are doing mini batch stochastic gradient descent. Mini batch stochastic gradient descent. That means even though you use mini batch, you are still, yes, adding the stochastic. Okay. So you can see what it means. Since the mini batch is sampled randomly from the training set, the expected value of the gradient remains the same. Okay, this is a bit technical. This is actually a bit, this is actually a bit technical, but we will try to understand it. It uses some knowledge of expectation, like statistics, a bit. But the idea is same. The expected value of the gradient you get in normal gradient descent will be the same in the case of this mini batch stochastic gradients. Gradient doesn't vary much. That's the idea. If this for the same problem your gradient varies much, then you are at trouble. Okay, you are at trouble. Why? Like people can ask, why for the same problem but using two different methods, your gradients are varying? Should be the same for the same objective function. The gradient should be the same. Yes. So therefore, you have to create a new method in such a way that the gradient doesn't change. Okay. So therefore, when you will see, even though it is sampled randomly, we will show that the expectation, like the average of the gradient you are doing it will be the same in case of mini batch and the original gradient. Okay, that is a bit technical, but you'll see. And one more important thing is like the variance of the gradient estimate will be reduced. So I hope when you are considering stochastic gradient descent, you saw that with replacement, the variance in the gradient is much more, isn't it? So therefore, if your method can reduce the variance in the gradient, it is a good method. And Minibatch is actually doing it. Because in Minibatch, the variance of the gradient reduced. Okay, because we are averaging over multiple gradients or over mini batches, multiple batches. I would say multiple batches. Yes. So we will see how much the reduction in variance is there. Okay, this is just a fact. I am keeping it. I'm not proving. So the how much, okay, you said that variance in your gradient has reduced. Okay, variance in the gradients has reduced, but there is no quantification how much it has reduced. So this gives a quantification that it decreases, like reduction in variance is proportional to 1 over mod b. Okay, fine. So if you, what does it mean? If you increase your batch size, then variance in the gradient is less. Do you understand? Can you, from this relation, it is inversely proportional. What does do you know about inversely proportional? Yes. Yes. So if you increase BT, if you increase the size of your mini batch, then variance in gradient should decrease. So therefore, you now know that if you are dividing into binning, if you are dividing into batches, it is preferable that you divide them into large batch. It is preferable that you divide into large batch. But there is a trade-off. There is a trade-off. You cannot increase it fully. Okay. Maybe someone can say that, yeah, I can increase. You said it to increase the mini batch. I will increase the mini batch so as to cover my full data set. Okay, no, that doesn't work. Okay, so there is a trade-off. There is a trade-off. This works till certain regime. After that regime, no. Okay, till certain regime it works. Fine. So therefore, this brings us to the next idea that yes, now you told that we should increase the mini batch size, but how we can choose the right mini batch size, okay, for our computations. So you can see larger mini batches, which we saw here. This means larger mini batch. This is larger mini batch. Larger mini batch can reduce your variance. Okay, variance is reduced, but increase in computational cost. Okay, so there is a trade-off, as I told you. You can increase your batch size, but that batch you will be giving to one CPU, right? That batch you will be giving to multiple CPUs. Each batch you will be giving to multiple CPUs. If you have taken a very big batch, then it will be a load to that CPU because it will have to run it for a longer set of training samples, isn't it? So therefore, it increases the computational cost. That is a trade-off. That is the only trade-off there. Okay. So yeah. So therefore, that is the trade-off I was talking about. That at some point, we don't know because it is highly non-linear problem. All these problems are non-linear problems. So therefore, there is no theorems. There is no theorems like, yes, at this point, it should reduce. At this point, it should not reduce. Mind you that whatever you have learned, the theorems and all, are mostly for linear theory. Okay, in computational science course in the last semester, there were theorems because I was teaching you linear equations, how to solve linear equations and all. They were linear. So it was easy to frame theorems and all, but these are highly nonlinear equations. Okay, these are highly nonlinear equations of multi-dimensions. Okay, so therefore there is no such theorem or anything like that. It is very hard to make theorems on this. At some point, therefore we write at some point. If you are in linear theory, it could have been a theorem. Okay. So therefore, at some point, increasing the mini batch size leads to minimal variance, but this comes at a trade-off that is increase in computational cost. Okay, we saw why. Because why this computational cost increases? The larger batch goes to one CPU. Each larger batch goes to one CPU or one GPU. So therefore, it has to do a lot of work. It would have been better if you could have made it smaller and given to each CPU. That would have been faster. So fine. So if you want, I can tell this, but we can skip it if you want. That we are trying to understand in this slide why the expectation of the full gradient, like why the gradient in gradient descent and the gradient in mini batch gradient descent remains the same, even though the method is different. Okay, even though the method is different. This is just a proof. This is just a proof. Maybe I can just go through it. Shall I go through it? Or yeah? Okay. So full gradient computation in full batch gradient descent. What we do? This I hope it is okay for you. I hope this you remember all the time. We have been writing this multiple number of times throughout. So what we do, suppose you have an entire data set D. You have an entire data set D. Data set D means your training sample, all the training samples you have. And our job is to pick X from those training samples, isn't it? Those training samples. So we are taking the expectation. Note that expectation is similar to the mean. Expectation is similar to the mean. I hope many of you still remember your BS statistics a bit. Okay, expectation is still the mean. If you don't understand expectation, this is a serious time to go home and learn about expectation. Okay, because this is the basic statistics, and most important to you, even if you go to the next version of deep learning or whatever course in your third sem. Okay, most important expectation you should know. Okay, expectation, and we are covering X vectors from the dataset D itself. And what we are doing, we are computing the gradient. Okay, so that is same as taking the averaging out, average over n training samples. Training samples in dataset D. Okay, fine. Where n is the where n is the total number of samples in the dataset. Fine. This is the full batch gradient descent. Full batch gradient descent. Okay, you know about it. Fine. And that I am denoting it by G. That I am denoting by G. Okay. G stores all the information of all the training samples. Fine. Let's come to mini batch. So this is the expectation you know now. In mini batch gradient descent, we select a subset BT of size B equals to mod BT. Okay. Each batch drawn uniformly at random from the dataset. Drawn uniformly from the dataset. Okay. So up to you. Now there are two questions. There are two different kind of versions of mini batch. If you draw uniformly and if you draw non-uniformly. Okay. That is a bit more, very much detail. We are not going to it. But same as stochastic gradient descent with replacement and without replacement, here also you have the same thing. Minibatch gradient descent, uniformly take the data set, data samples, or non-uniformly take the data samples. Which one is better? Not covering. Leaving that to you. Okay. So drawn uniformly at random from the data set, then the mini batch gradient descent is what I have given to you in the previous two slides. I hope you remember this. This was just written mod BT, nothing else in the previous. I hope you can check your notes. Okay. This was the gradient. This was the gradient. Okay. So therefore, you can see since the mini batch is sampled uniformly, each xi, that means from the training sample in the batch, this comes from each batch bi. Okay. Xi is coming from the batch bi. Okay. Xi is coming from the batch bi. Fine. So therefore, this xi, each xi is an independent sample from the full data set. No one told that this sample should be in batch 1, this sample should be in batch 2. It was all random. It was all random. So just it is very similar to picking that element from the whole data set. That is the only catch here. That is the only catch. Okay. So the binning you did, that was done in random. So therefore, you cannot claim that first element should be in batch 1. First element x1 can be in batch 5 also. Okay. So therefore, it is the same as taking the first element out of n samples. Okay. These two wording which I just told ensures, and what we have written mathematically is exactly the same. Okay. This ensures that the gradient in full batch gradient descent and the gradient in mini batch gradient descent are the same. Okay, because final thing is these two lines only. Finally, xi you are choosing from those n samples is independent. Think of this. X1 is if pick x1, does it depend on whether x2 is there or not? If I pick x1 from batch 5, does it mean X2 should also be there in batch 5. Therefore I say it is independent sample. It is an independent sample. Okay, it is an independent sample. It doesn't depend on other samples. Fine. So therefore, in many batches, you can see why. And this same case, what I told you, that take this first element X1 from batch 5, that is the same as that is the same as taking the first element from n samples, isn't it? Okay. So this means taking the expectation over the random mini batch, like this expectation of BT over the batch BT. Okay. So GT is the gradient when you take the mini batch BT. GT is the gradient over the mini batch. GT is the gradient over the mini batch BT. Okay. So you have to go through the notations a bit. Don't get lost with all these notations and all. This looks very careful, but it's okay. So expectation of BT, and the same thing we are doing. This is nothing but mod BT. This is nothing but mod BT. So this is expectation. This is the same as mini batch, right? What you have seen so far. This is the same as mini batch stochastic gradient is. Fine. Okay. Now by linearity of expectation, you can take this expectation inside. By linearity of expectation of something, expectation of a sum is sum of expectations. Fine. So therefore, I can take this expectation inside the summation side. You can see it came here. Fine. So I hope that is okay. Now we are using the beautiful theory. We are using that beautiful theory that since xi is drawn uniformly from the same data set D, so therefore it doesn't matter whether this expectation should be the full expectation. This expectation should be the full expectation, because each xi is a random sample. Is an independent sample, and it doesn't depend on any other samples in the data set D. Okay, therefore this expectation will be the same as the original gradient. Okay, so can you tell me what should it be? It should be 1 by mod BT, and how many times you are doing the sum over? You are taking how many batches? That depends. Yes. So therefore you can see why it comes G. You can see why it comes G. Fine. So therefore you can see why it comes G. So you can understand that expectation of BT over GT, this is from mini batch, as this is from full batch gradient descent. Okay. It's okay. Don't have to understand the full proof, but just the idea behind the proof. What is the idea behind this proof? The simple idea behind this proof was each training sample is an independent training sample. It doesn't depend, first training sample doesn't depend on third training sample. Third training sample doesn't depend on the fifth training sample. Okay. These are all sample set finally. Okay. And therefore, when you are taking the expectations and all these things, since they are independently related, like independent, they're independent to each. Therefore, the gradient, the full batch gradient, what value you are getting is the same as the gradient over the mini batch. Okay. And that ensures that your variance is less. Okay. So I also strongly suggest, if you don't understand this word, please go home, read it. Okay, this is the time where the important things you can refer to, you can know which are the important things. Unbiased estimator. Okay, this is one of the most important concept in statistics. One of the most important concept in statistics, and you need it. You need it, to be honest. This you can get in your interview questions. Okay, like expectations, you can get variance, mean, median, mode. From there it comes mean, median, mode. Suddenly it will come to expectation, variance, first moment, second moment, unbiased estimator. What is an estimator? Fine. These things we covered in this lecture today. Only the keywords. I'm giving it to you that these are the most important ones. Okay, so you have to know it. Fine. Okay. So you can see that this is crucial because it means that on average, matches will lead to the same parameter updates as the full data set, but with lower computational cost. Okay. Now the gradient is same. So you might ask, why not use the full gradient descent? Why we are learning all this? Then you can see mini batch gradient descent we saw reduces computational cost as opposed to your full gradient descent method. Okay. So therefore, even though the gradient remains the same, mini batch gradient descent is computationally much faster than the gradient descent. We saw like your full gradient descent is of time complexity order n, because you are taking the sum of all n training samples, gradient of all training samples. In mini batch, you are not doing it. In mini batch, it is of order of that mini batch. Okay. So therefore, it is reduced by some way. Okay, so this is about mini batch. So we'll see some code. I think let me go to that. Yes. Okay, so you can see that yeah, we are importing time, import time. That means we want to know with how much amount of time my code gets over, like a code gets computed, like it's finishes the computations. I want to know that time, run time. Okay, how much time it takes. Through that way only I can show you that 3 multiplication which one is better. Okay, actually in practice, you should not believe me, but we'll. So you can see what I'm doing it here. Yeah, import numpy, import torch. Fine. You can see like there are two things in CUDA. You will those who are taking, I think, parallel computing course. How many of you? Many are taking. Yes. So I hope you will learn this CUDA and all these things. What is CUDA? In Hindi it means something else, but yeah, yeah. But in English it means very nice things. Okay, so uh, CUDA like a device. We want to know code, CPU or GPU is used. Okay. So which one is available in your system? Which one is available in your system and which one you want to use in your program? Okay. So therefore CUDA, if torch.CUDA is available, else CPU. Okay. And then you're printing using device, which device? Okay. So since you can see the output of this code is CPU, that means it is using CPU. Colab is giving me free version. Colab is giving Google Colab is giving me free version. So therefore, I'm using CPU. Okay. Okay. So therefore, we are printing which device it is using. And since I'm using the basic feature of Google Colab, it will only give me CPU. Okay. It will not give me GPU. Okay. So if I had a premium version of Colab or I'm running this in my Python Python local Python, then yes, I can have one GPU or something like that. But if you're running in clusters, sorry, if you're running in cluster DGX, we have NVIDIA DGX in the university. So that is very powerful. We have DGX 800 and that is highly powerful. Like, of course, I am using CPU in that 200 or 300 CPUs are there for my work I can do is requires just 300 CPUs, but it has around 10,000 GPU cores. So if you are using GPU, I strongly suggest this is a very nice opportunity. So try to use DGX 800. Okay, NVIDIA DGX 800. That's a very nice opportunity, and you can write in your CV that you know how to run this on DGX 800. So this gives you a weightage because there are a lot of openings comes for HPC, high performance computing positions, whether in research, whether for a PhD, whether for a postdoc, whether for intern, whether for any engineer, whether for CDAC. Everywhere, if you have used this high performance computing, if you know parallel computing a bit, you stand out. So therefore, I suggest try to understand these things. initialize matrices on this selected device. You can see I am keeping a 256 cross 256 matrix a square matrix, and it is all zeros. It is all initialized to zeros, and the CPU. Okay, and B is randomized. B has 256 cross 256 elements, but with random entries. C is also the matrix with random entries, 256 cross 256. What I am doing, since I have B and C with random entries, I want to multiply these two matrices, and I am doing by using matmul. I hope you remember this from your bridge course. When I was showing you PyTorch, I was giving you this. Okay, matmul BC, that means it will do the matrix multiplication. Okay, it will do the matrix multiplication. Fine. We are using the torch thing, and A bring the result. A is matmul BC. So B into C matrix multiplication you are storing into A. Now A is no more zero matrix. It is something else. And we are printing the shape. Fine. Fine. So now we want to record the time instance for each of the three different kinds of matrix multiplication. That's the simplest thing we can try to understand all this mini-batch topics like vectorization, all these things. So what I'm doing here, I'm using class time. I have imported time, import time. Try to understand what you can do by importing time. So import time is something new to you. So I suggest Google it, import time, know what it can do. As you know, import numpy is NP. What import time does? Okay, try to do that. Okay. DSA. Oh, now. Okay. Yeah. I think that is more important in DSA class because you want to understand the time complexity. Computational order of n, order of log n, order of n square. Which one is faster? Okay. So therefore, you have class timer. Okay, you have class timer. I want to see how much time it takes for my code to run. Okay. So yeah, don't worry about all this. So basically, what we are doing is just just it can give you a time it takes to run the code. It can give you the average time. It can sum up other times in your whole code. That is, you can see sum. So if you run this, it will give you the total recorded time. Okay. If you want the average time it takes, you can use this. It will give you the average times. Okay. So similarly, there are cumulative sum of recorded times. So many possible things are there. Depends on your application, which one you want to use. Fine. So this is the timer. You can see elapsed time is 1.004 seconds. Average time is also 1.004 seconds. Okay, fine. This is a bit about timer. Okay, I want you to know. But now we'll come to our basic thing, which we want to show. Element-wise multiplication time analysis. Okay. So you can see timer.start. That means it has started. Okay. So we can do like for I in range 256, for J in range 256. What I am doing, each element-wise multiplication I am doing. And that timer dot stop. When it stops from start to stop, it will find the time it has consumed. You can see that it has taken around 2.966 seconds, more than that, 2.999966 seconds for this matrix multiplication. 256 cross 256 matrix multiplication. It is for you, it might not be that time consuming, but if you are working with big data sets, suppose maybe increase it by 10 and 10, 256 in 2560 into 2560. So it has to multiply 100 times. Can you say 296 seconds? 296 seconds is around how much time? Around 50 minutes, I think. Is it? No, sorry, 5 minutes. 5 minutes. So 5 minutes. So matrix multiplication taking 5 minutes. That is not good. That is not good. So therefore, you can see that when 3 seconds is low, but when you take larger data set, this is not the efficient multiplication. Now let us come to the faster strategy. That is one column at a time. I told you multiply matrix B with only one column of matrix C at every iteration. That's what we are doing here. B, comma, C, colon, comma, J. Okay. If you are doing it and we are doing the same start and stop, you can see how much time it is taking. 0.033. 0.033. It has reduced, I think, 1/10 It has reduced 1/10 because no, not even 1/10. It has reduced 1/100. 2.9. How much you get? 0.029. 0.029. And that is almost similar to this 0.033. Similar, I mean, not the same, but some kind of similarity. So 100 times you have reduced your computational time. Isn't that efficient? I hope that clears your idea. So therefore, this is something also I wanted to tell you. Flops. What do you mean by flops? Did you cover this in any class? Okay, should have been. So flops means like floating point operations per second. How many floating point operations you are carrying out per second? Okay, is a measure of computational speed of your algorithm. So therefore, any algorithm you take, it is good for you to actually take the timer. Okay, timer start, timer stop, and also to see the amount of flops. These flops we actually covered in computational science course without me telling you that it is flops. That is during LU decomposition, during Gaussian elimination. Okay, how you reduce the row operations and all those things. How many times you are multiplying, how many times you are taking the addition, how many rows you are considering. All that defines your speedness of your algorithm. Therefore, this flops is important. What is G flops? It's gigaflops. Okay, giga floating point operations per second. Right? So the 0.03 you got over here, the 0 estimation of the number of floating point operations needed for a 256 cross 256 matrix multiplication. Okay. The timer dot times which we saw stores the recorded time. So dividing by 0.03 by execution time gives you the G flops. Okay. So this is okay if you don't understand, but there is a metric of G flops. G flops is equal to total time divided by how many number of operations it is. It is a measure. It is a measure. I ask you to go through that. I ask you to go through that. Okay. So you can see if the performance is very low because it has 0.03 gigaflops, meaning only 30 million operations per second. Okay, you are doing 30 million operations per second. Fine. If the matrix multiplication is done column by column, it is even slower. That is 10 million operations per second. Slower optimized matrix multiplication results into achieving this many gigaflops, meaning that system is processing 891 million operations per second, which is significantly faster. Okay. So why I have given you this paragraph is to make you understand that what per second is going on in the computer. Okay. So you have a feel of what is going on at each second in your operations, in your algorithms. Okay. And why flops are important, even though we are not considering whenever we are writing a program, why they are important. Fine, and this is actually the code to find the gigaflops for this. Like you can see, we are matrix multiplying B comma C, start and stop. Gigaflop is 0.03 divided by, for each iteration, how much is the time. This you don't need to understand, but I want as a homework for you to understand these gigaflops. How to understand gigaflops measure. Fine. So yeah, that is all. So we after this lecture, maybe we can start after the break with momentum method, and we will start with a problem where gradient descent should be able to solve the problem, but we will see that gradient descent is not able to solve the problem. So I urge everyone to try this in Desmos or in Python, whichever is comfortable. 0.1. So, yes. So this is your objective function. This is your objective function. This is your objective function. And we will optimize this objective function. Obviously, you can know what is the optimized value for this function. What is the optimized value for this function? Why? Intuitively, it comes to your mind 0, 0, but to actually make it work out, what you should do? Yeah, you can compute gradient. Gradient descent is a way to go. But the first most important thing, if you don't want to enter into complexity, what you should do? Sylvester criterion. Because it's depending on two variables only. It depends on two variables only. I told you, if you have an objective function depending on two variables, straightforwardly you can use Sylvester criterion, which uses gradient, which computes gradient, which involves Hessian also. Do that, and after the break, revisit the Sylvester criterion, for this function, and let me know what is the order optimum. Is it a minimum or a maximum? Okay. And yeah, we'll see what is the disadvantage in this. We'll continue maybe after the break, is it?